In this video, we will learn some simple ways of calculating the areas of a cross-section accurately enough to be able to calculate the volumes of a section. One way of determining the area is using basic trigonometry. Let's start with the basic shapes. The most basic one is a rectangle. The area of a rectangle is the width multiplied by the height, as shown here. If a triangle is 5 meters wide by 2 meters high, then its area would be 8 square meters. That little 2 next to the m, that's square meters. So meters times meters are square. That essentially means you can fit 10 1 meter square shapes. That is, you can fit 10 1 meter square squares into the shape as shown here. You count the squares to see this is true. There are 10 squares there. Looking at the bottom blue one, if the width was 6 meters wide and the height was 2.5 meters, then the area would be 18 square meters. So we have a full 10 full 1 meter squares on the bottom and 6 half meter squares on the top. 2 half meter squares make up one full 1 meter square. So if you can imagine us joining the half squares to make a full square as shown here, which makes it more obvious that the shape has an area of 18 square meters. You can count them if you like. The other basic shape is a triangle. There are different types of triangles. One type is called a right angle triangle because one angle is 90 degrees. That is, it is a right angle. You can see that the right angle triangle is just one half of a rectangle, looking at that green triangle at the top. The width of a triangle is usually called the base, while the height is still called the height. This means that the area of a triangle is half of a rectangle. So the formula to calculate the area of a triangle is simply one half of the formula for a rectangle, which is one half times the base times the height. In this case, the base is 5 meters, while the height is 2 meters. So the area is one half times 2 times 5, which is 5 square meters. Now notice that we write square meters as meters with a little 2 next to it. That little 2 there is called a superscript, and it represents 5 meters squared. That's a meter times a meter. This formula works for other triangles as well. So in the case below, looking at the blue triangle below, the base is 4 meters, while the height is 3 meters. So the area is 1 half times 4 times 3, which equals 6 square meters. This works because this triangle is basically two right angle triangles as shown here. Let's calculate the area of the bottom triangle again using these two right angle triangles. The blue triangle has a base of 3 meters and a height of 3 meters, which gives an area of 4.5 meters, which is 1 half times 3 times 3, which gives an area of 4.5 square meters. While the yellow triangle has a base of 1 meter and a height of 3 meters, which gives an area of 1.5 square meters, that is 1 half times 1 times 3. Adding these two areas together gives us a total area of 6 square meters, which is what we arrived at in the previous calculation. Road earthworks cross-sections are usually more complicated shapes. The shapes for cut and fill embankments look a lot like this, those two shapes in the bottom right hand corner. This shape is called a trapezium. The Americans call them trapezoids. They have two sides which are parallel and two sides which are not. There are different types of trapezoids, and calculating the areas for them varies. Sideline cut and fills and cuttings and embankments have more complicated cross-sectional shapes, but you can usually calculate the areas by using more triangles or rectangles to make up the shape, then adding them all up, which is what we're going to do in the next slide. We will not be looking at these complicated shapes in this topic. In this topic, we're assuming that we've got a flat ground surface, which gives us a quite simple shape. So we're assuming that our earthworks just has cuttings and fill embankments and the existing ground is level. That means we end up with a trapezium shape like this. This trapezium can be cut into a rectangle and two triangles as shown here. The rectangle is shown in green. Its area is the width of the earthworks formation multiplied by its depth at that section. So, by the way, this is a fill embankment. So if we have a 10-meter wide formation and a 3-meter depth of fill, then the area for the rectangular area is 30 square meters, which is 10 multiplied by 3. The triangles are shown in blue. They are formed by the side slopes on the road. The side slope is usually measured as how many units horizontal the slope extends for every meter of depth. A side slope of 1 and 2 means that the slope moves 2 units horizontally for every 1 meter vertically. In other words, the horizontal width extends 2 meters for every 1 meter of depth, as shown in the bottom left-hand triangle and in the triangles we're using in the trapezium. From this, we can calculate the width of the triangle by multiplying the side slope by the depth. In the slide, we abbreviate that to S times D. So S is the slope and D is the depth. So let's look at these examples in the bottom. So if the side slope is 1 and 2 and the depth is 3 meters, then the width of the triangle is 6 meters. The area would be 1/2 multiplied by 6 multiplied by 3, which equals 9 square meters. If the side slope is 1 and 4 and the depth is 2 meters, then the triangle width would be 8 meters, which is 4 times 2. The area would be 1/2 multiplied by 8 multiplied by 2, which equals 8 square meters. If the side slope was very steep, then we would have a side slope of 1 in 0.5, or 1 in every half. If the depth was 4 meters, then the triangle width would be 2 multiplied by 4, which would be 2, which is 4 multiplied by 0.5. The area would be 1/2 multiplied by 4 multiplied by 2, which equals 4 square meters. So to calculate the horizontal distance, we're just multiplying the slope by the depth. Determining the area of the whole shape involves adding all of the areas together. So in the example above, we have a fill embankment with a formation of 10 meters, a formation width of 10 meters, a depth of 3 meters, and side slopes of 1 and 2. Notice that we looked at the 1 and 2 side slopes in the first triangle. There is a rectangular area of 30 square meters and two triangular areas, each with an area of 9 square meters. We calculated those in the bottom left example. There is a rectangular area of 30 square meters and the two triangular sections each have an area of 9 square meters. Therefore, the total area is 30 square meters plus 9 square meters for one side and another 9 square meters for the other. Adding these up gives us a total area of 48 square meters. So the area of that trapezium is 48 square meters. The process we have just gone through would be repeated for each section. When you have this much calculation involved, it is a good idea to develop a formula that allows you to just plug in the numbers and get the result rather than stepping through the process we have just done. So let's look at how we produce that formula. We need to define the variables. That is the numbers we use to get the area. And rather than saying road width all the time or slope, side slope, all that sort of business, let's just use letters. That makes it easier to write it all down. So let's say that the letter W represents the road width. Let's say that the letter D represents the depth of the section. And the letter S represents the horizontal distance the side slopes extend for each meter of depth. So that's much easier just saying S rather than horizontal distance the side slopes extend for each meter of depth. You'd get sick of writing that after a while. So we just write S. We then write the equations using letters instead of numbers to get a formula for the total area. The first line is just saying that the total area, so looking at this formula down the bottom here, total area A total, so that subscript total just tells us that we're talking about the total area, not the area of one triangle or area of another triangle. A total tells us that it's the total area. So the first line just tells us that the total area equals the sum of all of the areas, the sum of the two triangles and the rectangle. And we've expressed this as the formulas we developed in the previous slide. In the second line, we rearrange the letters, the areas, and find that since the two triangles have the same area formula, then we can just add them together, which is not surprising because the two triangles are just two halves of one rectangle. Finally, we simplify the formula by combining the triangles into one item, because they're the same, just two halves of one rectangle. And so they're just two halves of one rectangle, which is depth of D and a width of S multiplied by D. So we can simplify the two triangles into one item, which is S multiplied by D squared. D squared is that D with a little 2, and it simply means D multiplied by D. So let's try this formula on an example we looked at in the previous slide. The width W is 10 meters, the depth D is 3 meters, and the side slopes are 1 and 2. Putting those numbers into the formula gives us the same answer as we got in the previous slide, 48 square meters. It's not surprising as we're basically doing the same process except using a formula to allow us to do it faster. So up until now, we've just looked at embankments, but what about cut areas? The same process is done for cuts. There is no difference in an area that is to be filled with soil, as is the case with a fill, and an area that needs fill to be removed, as in cuts. That's still the same area. So here is the ground level, and here, so we've got the ground level at on the top and the road level at the bottom. So it's basically an upside down version of the trapezium we used for the fill embankment. We can use the same process and the same formula we used before to determine the area of this cut. So if we have a cut with a formation width of 10 square meters, so that's the bottom part, and a depth of 2.5 meters, not 2.3 meters, and side slopes of 1 and 2.5, we end up with a total area of 33.225 square meters. Now we'd round that up to 34 square meters because we're not accurate down to square millimeters. We're not that accurate. We're accurate to plus or minus maybe 1, 2, 3, maybe even 10 square meters. So you need to be aware of that. Don't write everything down to lots and lots of square meters because lots and lots of decimal points because you're just not that accurate.